In this video, we will talk about a very nice quantum algorithm called Simon's algorithm. So Simon's algorithm is actually a hybrid algorithm, which includes quantum and classical parts. It's not all around quantum algorithm, but it also includes classical parts. But first, we will talk about the quantum part of the algorithm and what the problem is. Now, consider the function f from 0, 1 to the n to 0, 1 to the n. Okay, so function f from binary strings of n-bit length to the same set, such that f of x equals f of y if and only if y equals x or y equals x or s for some hidden string s. So the values of f in fact repeat themselves in some pattern determined by s, and we call s the period. So this is called the period of f. And Simon's problem is to find this period s. So this is Simon's problem. And let me give an example and what I mean by a period. Consider the example when n equals 3. Okay. Okay, so let me draw a table and let me give an example, a function from 0, 1 to the 3 to 0, 1 to the 3. So suppose that our function f is defined in such a way that on input 0, 0, 0, it outputs 1, 0, 1. And on input 0, 0, 1, it outputs 0, 1, 0. On input 0, 1, 0, it outputs 0, 0, 0. 0, 1, 1 maps to 1, 1, 0. 1, 0, 0 maps to 0, 0, 0. 1, 0, 1 maps to 1, 1, 0. 1, 1, 0 maps to 1, 0, 1. And 1, 1, 1, suppose it maps to 0, 1, 0. Now, in this case, you can see that the output of f occurs twice. So it's a 2-to-1 function. So you can see that, for instance, 1, 0, 1 appears twice. 1, 1, 0 appears twice. Okay. Okay. So in this case, you may see that s is in fact equals to 1, 1, 0. Because why? Well, take for instance 0, 0, 0. If you XOR 0, 0, 0 with 1, 1, 0, then you get 1, 1, 0, right? And f of 1, 1, 0 is again 1, 0, 1. Right, so these two pair with each other, okay? So in this case, s is equal to 1, 1, 0. But may not be always easy to find s. And in fact, it's not for classical algorithms. If s is all zeros, well, that means the function must be 1-to-1, right? But otherwise, then f is 1-to-1. But otherwise, f is 2-to-1. Now we suppose that our function is 2-to-1. Assume that the given function f is 2-to-1. Okay. So in that case, S is different than all zeros. And the problem is to find this S value, the period S. Now, classically, how many steps do we require to find this period given an arbitrary function f? Well, we need to evaluate f on different binary strings, and after each evaluation we need to see whether that output has already been found earlier. If we ever find two inputs, x1 and x2, let's say, such that f of x1 equals f of x2, then in fact we are assured that by definition x1 is equal to x2 XOR s for some s, right? And then we can obtain s here by XORing both sides with x2. So then we take the XOR of both sides by x2 and obtain x1 XOR x2 equals x2 XOR s XOR s2. But then these two cancel each other. x2 XOR x2 is equal to 0, right? And then what we left is basically s is equal to x1 XOR x2. Okay, now if the function is 2 to 1, then we have to evaluate. We won't have to evaluate the function for more than half of the inputs before we get a repeat. Right? If we evaluate the function more than half of the strings, and if we still cannot find a match, we still not find a duplicate, then we know for certain that the function f must be 1 to 1, and so this period value s must be all zeros. So in the worst case, we need to evaluate the function for at least half of the inputs plus 1. So in the worst case scenario, it's in the order of 2 to the n, classically, right? Quantum algorithm, Simon's algorithm, solved this problem in the order of big O n. So given such function, 2 to 1 function, we can find the period of the function, the period value s, in the order of big O n using Simon's algorithm. I'm going to give the quantum part of Simon's algorithm first, and in fact the entire algorithm consists of evaluating this quantum part a couple of times. So we start with two registers. Okay, the first register is set to all zeros. I'm making this bold to indicate that this is an n-qubit register. Okay. I'm going to start with two registers, each set to zeros of n-bit length. Okay. And I'm going to apply an n-bit Hadamard transform to the first register, n-bit Hadamard transform. And then I'm not going to do anything about this. Okay, so suppose that this is my UF, the quantum version of the function f given as a black box. And in the output, I'm going to apply another Hadamard, an n-qubit Hadamard transform. Okay, and then I'm going to measure the first register. So let's indicate the states. Let's call this stage psi 0. Let's call this psi 1. Let's call this psi 2. And let's call this stage psi 3. So let's explicitly try to write each state. In this case, psi 0 will be equal to boldface 0, 0. Okay. So the first register on state 0, second register is on state boldface 0, each of length n. They're all 0. And then we apply Hadamard transform on the first register. And then we get strings of all n-bit lengths, right? So then psi 1 will be equal to 1 over square root 2 to the power n summation boldface x. This is an n-bit string. So we have a set of all n-bit strings in the superposition. And the second register we have all zeros. Okay. So now we have to evaluate psi 1. We have to evaluate UF on the state psi 1. So fortunately, we have all zeros in the second register, so things are a bit more easy. And then we get psi 2. So psi 2 will be equal to 1 over square root 2 to the power n summation x in 0, 1 to the n. And then we have x in the first register, and then we have f of x. So this will be our output after we evaluate UF. And then psi 3 will be the state after we apply the Hadamard transform, n-qubit Hadamard transform on the first register. Okay. Now it will be the same as earlier. The behavior of an n-qubit Hadamard transform on the superposition of all n-bit strings will be written in the form I gave earlier, right here. Right. Yes, similar to this form. So then psi 3 will be equal to 1 over 2 to the n summation x in 0, 1 to the n. And then we have z in 0, 1 to the n. And then we have a minus 1 to the power x times z phase. Okay. On the first register we have z. Second register is f of x. All right. So since the function f is 2 to 1, we have exactly two x's. So let's call them x1 and x2. We have exactly call them x1 and x2. So these are n-bit strings such that f of x1 equals such that f of x1 equals f of x2. And we can actually write x2 in terms of x1. x2 is simply so since x2 is equal to x1 XOR S, we may rewrite psi 3 by setting x1 and x2 apart and write x2 in terms of x1. Okay, so here I'm going to separate, I'm looking at psi 3 now. I'm going to separate x1, the factors x1 and x2 apart. And I'm only going to write the amplitudes involving x1 and x2. Okay, so let me rewrite psi 3 as 1 over 2 to the n summation. I'm only going to consider x1 and x2. Okay, and then I have z. Okay, so setting x1 and x2 apart, I have minus 1 to the power z times x1 plus minus 1 to the power z times x2. And then I have the basis state z in the first register, and then in the second register I have x1. I could also write x2 here. I mean, it doesn't matter because fx1 and fx2 are equal to each other. Okay. All right. So now we know that where x2 equals x1 XOR s. So I also know this. Okay, this is given. So let's look at the amplitude of this basis state. I'm looking at this expression now, the amplitude of z f of x1. All right, so I'm asking, when do I get 0 as the amplitude of z f of x1? So the amplitude, the coefficient of this basis state is 0 when this expression here is 0, right? But let's examine this expression in more detail. This means that this expression is 0 when its equivalence is 0. And when I say it's equivalent, I mean replacing x2 by x1 XOR s. So let's substitute. This expression is equal to minus 1 z times x1 plus minus 1 z times x1 XOR s. Okay. But this is equal to, so I'm distributing multiplication over XOR minus 1 to the power z times x1 plus minus 1 to the power z times x1 XOR z times s. Taking this further, this last expression is equal to minus 1 z times x1 plus minus 1 z times x1 times minus 1 to the power z times s. Okay, the common factor is, common exponent is, the common base is minus 1. Okay, so then the amplitude of this basis state right here is 0 when this expression is 0. So but then what does that mean? In order for this expression to be 0, z times s must be 1, right? If z times s, if the inner product of z and s is equal to 1, then the above expression is simply 0. So if we measure the first register right here, if we measure the first register, z's, I will only observe those z's which are orthogonal to z. That means I will also I will only observe z's that satisfy, if we measure the first register, we will only observe z's such that z times s is equal to 0. So that means we will only get to observe such z values which are orthogonal to s, right? So then, but this determines a subspace which s must lie on. And remember, z and s are n-bit strings. So I can in fact collect n many samples here, right? So evaluate this circuit n many times and collect n many different z values. Satisfying this equation, right? Because we will only get to observe those z's which are orthogonal to s. And then we get n many linear equations. Right? We get n many linear equations, and then finally we can apply classical methods we know from linear algebra, like Gaussian elimination method, for example. And then using those elimination methods, we can determine, using classical Gaussian elimination method, we can solve this equation, right? And we can find s. And what we did is that we evaluated the circuit, the quantum circuit, n many times, right? And Gaussian elimination method takes in the order of n. So then we get a complexity of big O n to solve Simon's problem. And interesting part is that it was also shown separately that Simon's algorithm is optimal. In the sense that it at least takes n many steps. So it's also omega n. So in this sense, Simon's algorithm is optimal. Okay, so in the next video we will talk about a quantum search algorithm called Grover's algorithm. So I'll see you in the next video.